25 peer-reviewed papers and receiving over a dozen awards for research and scientific communication, including the AAPG JC Ken Sproul Award. Mark joined Petronas in 2018, where he leads their Pore Pressure and Geomechanics department, and he is currently the AAPG president for the Asia Pacific region. So Mark, thanks a lot again for accepting our invitation, and feel free to start us off whenever you're ready.
Thank you, Gabriella, and thank you all very much for inviting me here today. Just give me a minute to share my screen, everyone. Can everyone see that okay?
Yes.
Fantastic. So yeah, good afternoon or good morning, wherever you all are in the world. As you heard, my name is Mark Tingay. I'm the head of Pore Pressure and Geomechanics at Petronas. And it's my pleasure to be here this evening to present about the geomechanics and pore pressure issues associated with salt. Now, I have to start with a disclaimer here, which is that I'm not a salt expert in any way. I've been doing geomechanics for a very long time and pore pressure for a very long time, both in academia and in industry. And I've dabbled in salt here and there and had to work in salt provinces around the world, but I'm by no means a salt expert. And the idea of this presentation is not as the sort of groundbreaking work on salt, but it's more of it was actually designed for internally in Petronas to help non-experts in geomechanics and pore pressure to understand the difficulties and the complications that we face when we're drilling near and around and inside salt. So this is more of a broad summary and overview of the challenges we face and sort of an introductory level talk. For those of you who know me, I'm actually much more of a focus on mobile shale and mud volcanoes, and my Twitter is all mostly about mud volcanoes. But today it's very kind of Clara and the AAPG Salt TIG to invite me to give this presentation. So I'm a little bit out of my depth on salt. I'm by no means a salt expert, but I hopefully will give you a very nice summary of the challenges we face and on a sort of introductory level. What I'm going to go through today is a summary, first of all, just to introduce a topic, give you an overview of some of the common problems that we have in doing pore pressure prediction and geomechanics in and around salt, and sort of explain mechanically and rheologically why dealing with salt is such a challenge, particularly for geomechanics. I'll then talk about pore pressure issues and loss issues that we have when we drill wells. I'll talk particularly about how salt controls pore pressure and losses, and how salt also impacts our pore pressure prediction and how we try to predict pore pressure before we drill wells, which is a key step we have to do in planning any drilling operations. Then I will talk about geomechanics side of salt, and in particular, I'll talk about wellbore stability and salt creep, and the complications that salt gives, such as how stresses are impacted around salt. The Earth's stress state is impacted by the salt bodies, and salt creep itself and how that causes issues associated with drilling operations, before wrapping up with some conclusions. So one of the things that we find, what we often find when we're drilling through salt is that we can have challenges and issues all the way through the well, from prior to the salt, particularly as we're entering the salt body. Drilling in salt has complications. Then we have further complications when we exit the salt. And even once we've exited the salt and then drill into other sequences that could be quite a way beyond the salt, we have additional complications that can arise related to the salt body. So salt poses a lot of challenges: entering the salt, inside the salt, exiting the salt, and then in the sequences below the salt. And I want to go through a number of those during this talk. I find this is actually, this slide by Steve Wilson and Friedrich from 2005 is a really nice summary of the common problems that we have drilling near and through salt. So we can have often rubble zones or fractured rocks, highly fractured rocks in the carapace above salt bodies that can lead to losses or can lead to stuck pipe issues. Then when we actually enter the salt, we can have a number of issues associated with either things like high pressure trapped in seams, or potentially blocks or rafts of sediments trapped inside the salt that can contain significant pressures. We can have welds that can relate to creep or creep just during the normal salt body, as well as we can have quite variable mineralogy, with some salt mineralogies creeping or flowing at a faster rate than others. Once we actually drill out of a salt body, we can have issues such as salt that was not predicted, so invisible wings or salt bodies that were poor or difficult to resolve below the salt. We can have complicated stratigraphy and structure. We can have tar bands. We can often have pressure increases or regressions, as well as further rubble zones that can be associated with losses. So we have a lot of issues in and around salt. And while this sort of model is the classic Gulf of Mexico kind of salt body, we have a lot of other different types of salt bodies around the world, and different salt tectonic regimes that have their own challenges. So why actually is salt an issue? And this kind of comes down to the dirty secret of geomechanics, which is that while geomechanics is often a lot of assigned workflows and equations and things you can go through to build a mechanical earth model, the fundamental foundation of most geomechanical workflows is the assumption that the rocks are elastic, that they behave in a brittle, elastic way. So they have a very simple linear relationship between stress and strain. And that helps us to boil down the maths into things that are a lot more simple to understand, the things that we can predict from, or we can measure from lab measurements, as well as from measurements in the well. However, salt is not a perfectly or an elastic material. Salt has very complicated mechanical properties, and it can vary. Those mechanical properties vary a lot with both strength and strain. So the strength and strain of the rock of the salt depends on its mineralogy, its composition, its fabric, temperature, how pure it is, and the applied stress, or particularly the differential stress and the strain rate that is applied to the rock, to the salt. Broadly, we classify salt as being viscoelastic or viscoplastic. That is, that it deforms it elastically, like most normal rocks. It behaves elastically and will typically break brittly in very low differential stresses. So when it's under very low stress difference, differential stress is the difference between the maximum and the minimum stress that's being applied to the rock. So when all the stresses are quite close together, the rocks will, and when it's under a very low stress, salt tends to deform brittly. If you take salt at the surface and smack it with a hammer, you know it'll shatter. However, under even just moderate differential stresses and even relatively low temperatures, salt starts to behave viscously, and it will, or plastically, where it can creep and flow like a thick viscous fluid. And so it will behave in a very different manner under the geological conditions that we're often drilling in and we're often exploring in. Salt's further complicated by its properties being affected by mineralogy, not just the mineral itself, but also the purity, how much water is in there, temperature and strain rate, how fast it's deformed. Salt tends to be weaker and deforms more plastically at high temperatures. It tends to be weaker at lower strain rates and stronger at higher strain rates. And its behavior is also impacted by the composition, the purity, the mineralogy, the fabric, lots of different things, all of which are often at a very low, very small scale that are extremely difficult to predict in advance of a well. So before actually drilling, we don't have any real knowledge of what the detailed properties inside that salt are. So salt mechanical properties are complicated, not just because they have a lot of variability to their mechanical properties themselves, And it's also very hard to assign a model to their behavior. While there's a couple of very common standard ones out there to explain how salts behave mechanically, they don't always fit that well. And if you look through literature, there's literally dozens upon dozens of salt models that have been proposed to describe mechanical behavior from lab specimens. So it's very, very difficult to really predict in advance what sort of salt we're going to see. What are all those very fine scale aspects of it that will control its mechanical properties? And then even if we have that, to make a prediction about how its mechanical properties will vary and how it will actually deform under in situ conditions. So lots of difficult mechanical behavior models, very difficult and poorly defined and often hard to predict inputs. So it really is a very complicated process and a very challenging medium to work with, rock to work with. I want to move on to pore pressure first. So let's talk about how salt has a big impact on pore pressure. And now the key here is that salt doesn't generate the overpressure. So we often get a lot of overpressure, a lot of high or abnormally high pore pressures in salt basins. It's not actually generated by the pressures aren't generated by the salt itself. However, in order to generate very high pressures, you need a seal to confine those pressures, to hold back those pressures. It's just like thinking about a hydrocarbon play. You don't just need the source of the hydrocarbons, you also need a trap, you need a seal. And it's the same with overpressures. For overpressure, you need a source, a generation mechanism for the overpressure, but you also need a seal to hold the overpressure. And the amount of overpressure that can be held is directly proportional to the quality of the seal. And salts are an extremely good seal. Salt basins have fantastic geological conditions for overpressure generation. You've got lots of really rapid deposition rates, particularly as some of these mini basins drop down very rapidly through the salt withdrawal. Lots of low permeability sequences, and they can often be associated with quite high tectonic stresses, all of which are the ideal conditions for generating overpressure. And then you've got the salt, which is a fantastic rock for preserving overpressure, for sealing overpressure. Salt's extremely low permeability, is excellent for trapping and maintaining overpressures over millions of years. So we often have very high magnitude overpressures in salt regions. And so this can be a big risk, particularly when we drill out of the salt. So when we go from the salt and exit the salt, it's always a challenge to try to predict what the pressures are likely to be as we exit a salt body. And the pressure can increase extremely rapidly. So with very little warning, we can go into a sudden rapid jump or sudden sharp jump in the pore pressure that can result in well control being lost almost instantly. And it's not just prediction of the pressure, but prediction of the base of the salt that is also a challenge. Of course, with imaging being difficult at the base of salt and below salt, we have less control on predicting the base of the salt depth as well. So being prepared for when that change from salt into potentially overpressure sequences might come about. Inside the salt, we actually don't often have too many problems with pore pressure. Salt being effectively a viscous fluid results in the pressures inside the salt being essentially lithostatic, so roughly equal to the vertical stress. Extremely high stresses and fluids. Essentially, the stresses and the fluids are all equal. That's what a lithostatic stress state means here. So they're all lithostatic, they're all approximately equal to the overburden stress, the weight, the stress generated by the weight of the overburden. And all the pressures, all the stress inside the salt are effectively lithostatic inside the salt. Now that's huge pore pressure, but that won't generally cause an issue when we drill a well because there's no permeability. So we can drill through extremely high pressures, even under balance, if there's no permeability. If there's no permeability, we don't have a well control because the fluids can't flow out of the salt to generate a kick. However, salt is not just one bubble of salt. It's not just perfect, clean salt. There's a lot of impurities inside it, and it could also capture big rafts or big chunks of sediment inside it. In fact, I'll drop back to my title slide here, which I didn't really put a figure on. I didn't really put a caption on, but this is actually a salt body in Iran with overlain by faulted sequences, by thrust faulted sequences. I've faded it out so I could have the text, but this white zone here and everything below it is actually salt. And inside it, you can see these big chunks of red rafts of sediment that have been entrained inside that salt body. And that's not an unusual thing to have big rafts or big chunks of sediment inside, completely trapped inside the salt body. And if we drill into those, they can have permeability and they will be overpressured in the same way or in a similar way to the salt around it. They generally have very high pressure, and we drill into them, we can easily take a kick or have a well-controlled incident. Typically, they're relatively small volumes of fluid, so that if there is a kick, it tends to be fairly short-lived. However, they can be quite large and they can be a hazard when we drill through salt. And in addition to inside the salt, when we drill below the salt or adjacent to salt, we have additional complications. We first of all can have very steeply dipping reservoirs. So the movement of the salt can significantly deform the rocks around it. We have a lot of structural complexity adjacent to salt bodies. And those steeply dipping rocks can allow fluids to be overpressed, to be plumbed into deeper sequences and have overpressures migrated or transferred into the crests of reservoirs that are often our petroleum targets. We also can have excess pressure from additional mechanisms as well in the sequences below the salt. A few examples of that, and I really want to sort of what I still think is probably one of the most incredible and quite scary blowouts that's ever happened in history is this one, the 1956 Albors 5 blowout in Iran. Now, this is actually one of the biggest blowouts onshore ever in the petroleum industry. It flowed over 5 million barrels of crude oil, a rate of 60,000 barrels per day for 82 days before it bridged itself. So it essentially, the wellbore underground collapsed and it bridged itself, so sealed itself off, which sometimes happens. However, what was quite amazing is that the work that they looked at after this incident found that they lost control of the well after penetrating the salt by no more than 5 centimeters or 2 inches if you're dealing with the imperial units. So this well, Albors 5, was targeting this subsalt carbonate sequence, subsalt limestone sequence, fractured limestone sequence. After drilling through tertiary clastics and then through 380 meters of the evaporites, they hit that fractured carbonate sequence and the well immediately blew out. They lost control after drilling no more than 5 centimeters. So a few seconds really after penetrating that reservoir. It's like pricking a balloon. They went from the salt, which would have been overpressured, but with no issues. They expected high pressure, so they drilled into this with 17.3 ppg mud, which is extremely high. We typically would not drill with anything nearly that high in most well operations. That is a very dense mud weight. However, even with that dense mud weight, the pore pressure well and truly exceeded 17.3 pounds per gallon and blasted that drilling mud out of the hole, followed by this 82-day, 5 million barrel kick. So it gives you an idea of just how quickly things can change. That you penetrate through the salt, even if you're quite prepared, just penetrating through the salt and being under balance can be an instant disaster. Let's have a look at an example of pressures inside salt bodies. So looking at the rafts or stringers that we sometimes get inside salt bodies, or intrasalt rafts or stringers. And there's some really nice work that's been done on this by Peter Kulka's group and others over the years on the Ara salt in Oman. Now, as I mentioned before, salt being essentially impermeable viscous fluid means that all the fluid pressures and stresses inside the rock are basically equal and close to lithostatic, so close to the weight of the stress generated by the weight of the overburden. However, we tend to not have any issues drilling through the salt. We don't tend to have no pressure, pore pressure issues drilling through the salt when there's no permeability. No permeability means no pore fluids can flow into the well. But if the salt bodies contain isolated rafts or stringers that can be fractured sequences or sedimentary or permeable sediments, then they will also share the same high pressures that are in the surrounding salt. And these stringers inside some of the Oman salt bodies are essentially their own self-sourcing petroleum system. These stringers can contain a source rock and a reservoir, and the salt makes a seal around it. So these can be their own actual self-sourcing reservoirs that can be targeted. However, what's been found is that drilling into some of those isolated isolated stringers or rafts encounters quite significant pore pressures. And so here's an example of let me just change to the point. Here's an example of what's seen in the Ara salt, where they've taken a lot of pore pressure measurements in stringers that are connected to the surrounding sequences, and so tend to be roughly close to hydrostatic, versus stringers that are inside the salt and are disconnected from the surrounding formations, tend to be very highly overpressured, right up here just below the lithostatic. So when we drill into these, we sometimes have well control issues if we're not prepared. But now I want to talk a bit more again about high pressures trapped against salt flanks, because that's another major challenge. Now, a lot of hydrocarbon plays, a lot of exploration targets that we have when we're drilling near salt bodies, use the salt diapir, the flank of the salt, as a seal. So we often will look at a reservoir that's or a sand zone that's actually abutting against the salt. The salt and the overlying shale is essentially the seal for the reservoir underneath. So we often target reservoirs that are quite close to the salt body, because the salt body itself tends to be very close. It's the crest, and all the hydrocarbons have gone to the crest, so we drill near the crest. However, drilling near the crest is also where all these tilted formations, these formations can often be tilted or overturned or steeply dipping, are able to have potentially the highest pore pressure. So when we have sedimentary sequences that are deposited and overpressure is generated, overpressure is not just a static phenomenon. If you generate overpressure, that overpressure wants to escape. It doesn't want to be there. It wants to get back to normal pressure, hydrostatic. So if there's any ability for the fluids, for pressure to dissipate or fluids to flow through the petroleum system, then the pressure can be transferred into along sequences or long beds, or up faults or fractures into shallow formations. So pore pressure is not a static phenomenon. It doesn't just occur in the rock it's generated in. It can also migrate and be transferred into other sequences. And salt basins are very good for fluid flow through the system. So this is a very nice study I found by Roslöfer. I'm terrible at pronouncing the name. I do apologize if anyone knows them. But it has a really great summary of schematic summary of how classic migration pathways through salt zones. And this is also a really good analog for how overpressure can be transferred and migrate through the petroleum system or through sedimentary systems. So overpressure can, any of these steeply dipping potential reservoir zones adjacent to the salt can be plumbed into deeper petroleum overpressure systems, overpressures, as well as having hydrodynamic influences associated with the dipping layer, what's called a lateral transfer effect and a hydrocarbon buoyancy effect, which essentially migrates pressure to the crest of the structure. So we get excess pressure at the crest of a dipping reservoir, and we get a pressure reduction at the base, down deep at the flank or the base of a dipping reservoir. So drilling near the crest of the reservoir is not just in a high pressured rock, it has an excess pressure and then an additional buoyancy pressure from any hydrocarbons, making it an even sharper pressure increase, pore pressure increase as we enter that reservoir. So this, some of these aspects are quite predictable if we can calculate the hydrodynamic effects if we have a very good understanding of the geometry of the reservoir and the geometry of the rocks. However, that's a big challenge below many salt bodies due to the imaging effect, due to it being very difficult to image below salts. So this is why where geology is absolutely a critical element of doing pore pressure prediction in this day and age. Back 20, 30 years ago, pore pressure prediction was very much dominated by geophysics. It was very much a purely seismic velocity-based process. But over the last 20 years, it's become much more of a geological-based process, really being first and foremost founded on our understanding of geology in our play and from our basin to our prospect, in order to really properly constrain the potential pressure scenarios and the greater complexity that we know pressures can show in sedimentary basins. In addition to pore pressure issues, one of the biggest issues we face in drilling near salt bodies and exploring near salt bodies is actually losses. So where we enter some sort of fractured or permeable formation or zone where our drilling fluid escapes from the well. If we lose significant amounts of drilling fluid, we can't keep the drilling mud topped up in the well, we lose the hydrostatic column, which is the pressure inside the well bore that is keeping overpressure or keeping high pressure fluids out of the well bore. So that mud weight, we have to keep the pressure inside the well higher than the pore fluid pressure. Otherwise, fluids from the rocks come in, and that's what leads to a well control incident and potentially a blowout if we can't keep that under control. Losses are often the first trigger to a well control incident, because if we have losses in one part of the well, it makes it very difficult to keep a sufficient hydrostatic column, a sufficient column of mud in the well in order to offset the pressure in other parts of the formation or in other parts of the well. So losses are a really huge issue and often one of the most serious issues we face, because we know that it can be the first domino that then leads to many, many worse things. And unfortunately, drilling near and around salts is at high risk of loss zones. So salt movement, the actual flowing of salt, particularly as it flows up and into a diapir and into sheets and canopies, that motion of the salt tends to significantly damage all the rocks around it. So that salt moving through and forcing its way through the rocks, through the surrounding country rocks, the surrounding sediments, tends to cause a lot of damage. We have a lot of intensely sheared zones near the necks of salt bodies. We can also have a lot of rubble zones, both at the canopy and the carapace above the salt and below the salt. So we have rubble zones, intensely deformed zones. All of these can have a lot of fractures and a lot of permeability and can be classic zones for where we have losses. So rubble and gouge zones are commonly associated with drilling issues. And big study from the Gulf of Mexico by Sala et al. In 2013 found that about 2/3 of all subsalt penetrations in the Gulf of Mexico encountered rubble zones. And many of them had major issues associated with losses drilling through the rubble zones. Sometimes we drill through the rubble zones with no problems. Sometimes we have significant losses, and it varies. So in particular, near the necks or the feeders of salt bodies it was found almost 90% of the wells that drilled through feeder zones or near feeder zones encountered gouges or rubble zones. I also forgot to mention that the highly deformed shales and sequences that we get near salt movement can also be associated with gumbo shale, so very weak shale that essentially flows into the well and can trap around the drill bit. So that can cause significant issues such as stuck pipe. Now, salt doesn't just have those challenges. In addition to the actual geological aspects and elements or issues that salt can cause, such as high pressure, rubble zones, and loss zones, salt itself adds further complexity to when we do pore pressure prediction because it complicates the inputs that we use in predicting the pore pressure. So pore pressure prediction requires really reliable geological models and geophysical attributes. And that's just very difficult to get around salt, particularly below salt zones. Pore pressure prediction really needs accurate and very high resolution seismic velocities, often specially processed velocities well beyond the processing that's done just for seismic imaging. Pore pressure prediction also requires very detailed knowledge of the geology to understand how overpressure can develop, how it can be transferred, and how it can potentially be dissipated in the sequence and over geological time. And pressure prediction also requires really reliable estimation pre-drill of the lithologies, their potential permeability, their mineralogy, their fluid types, such as whether it's water, oil, gas, and the amounts. And of course, this is why we're exploring. We don't know those things. We're exploring to try to find out those things, not just why is there hydrocarbons there, but also all the other geological elements that can help us then explore other parts of the basin. But before we drill the well, we have to make predictions about all these things. And all of them have significant uncertainty, and that uncertainty is even greater below salts. Subsalt velocities and subsalt attributes are very difficult and often less reliable and lower resolution. Lower resolution, less reliability makes the uncertainty window on our pore pressure prediction greater. And that's a bigger challenge then, not just for drilling the well, but also constructing and planning the well. And geological models and understanding the complexity below salt and in sequences adjacent to salt that have often been highly deformed is much more complicated. So pore pressure prediction also requires really extensive geological and geophysical work in both the overburden and the underburden. And it's worth noting that often the focus when we do exploration wells is all about the reservoir. It's all about the reservoir. We collect a gazillion logs and core plugs and do all our tests and all of our focus on the reservoir and maybe a little bit of the seal, but often not even that. It's all the reservoir. And very little emphasis is actually put on the sequences, the often 3-4 kilometers of rock or more that we have to drill through before we actually get to that reservoir. Often there's a lot less sampling done, there's a lot less logs, less quality, less measurements of things like pressures, less core. So the zones in which we actually really need the information to do pore pressure and geomechanics are the zones that we tend to actually not collect a lot of data. So that adds further challenge and complexity and difficulty to pore pressure prediction, which then flows on to how the difficulties in drilling wells. So really the key to improving our pore pressure prediction and improving our drilling safety and our drilling performance in salt basins is to tackle all of these issues, to really look at better ways that we can do for imaging of the salt, collect data so that we can better understand the salt, better understand the sequences around the salt, take a much more holistic view to understanding the geology in a larger scale and not just purely a focus on the reservoir. All right, let's move away from pore pressure now and let's focus on geomechanics and look particularly at wellbore stability and creep. Now, before I even talk about wellbore stability and creep, I sort of want to really highlight some of the key issues associated with salt for geomechanics. So the first is that it's one of the first things I want people to take away from this talk is that salt's mechanical properties have an impact far beyond the salt body itself. So the issues we have with salt are not just inside the salt body or even right near the salt body. They can be kilometers away from the salt body. Due to the salt itself impacts and can change the stress state around it. So the salt actually varies the Earth's tectonic stresses in the vicinity of that salt body. And that's because salt is weak. Salt is an extremely weak process. It effectively is behaving like a viscous fluid. And one of the theories of one of the key tenets of elasticity and how salt acts in elastic media is that the stress will get disturbed by any major mechanical property contrasts. In essence, a very simplistic way of looking at it is that the stress must be, one principal stress must be perpendicular to any free surface or major discontinuity in elastic properties. Salt is a major discontinuity. And so the Earth's tectonic stresses tend to rotate in the vicinity of salt so that one tectonic stress will be close to perpendicular and others will be close to parallel to the salt rock interface. Now, the degree of stress disturbance varies due to the size and the shape of the salt body and the size of any mechanical property contrast. But as a general rule of thumb, a salt body will, or a mechanical rock property contrast will influence the stress out to 3 diameters of that body. So if we have a circular salt body, the stress field can be deformed or impacted by that salt body out to 3 diameters away from that salt. So if you have a 1 kilometer diameter salt body, which is not huge, a 1 kilometer diameter salt body can impact the stress state, the Earth's stress state, even drilling 2 or 3 kilometers away. Salt is the other aspect with salt is that it doesn't just impact the state of stress, the sort of static state of stress today. The salt's ability to creep and flow and potentially over even relatively brief hours to day timeframes can have further impacts on drilling operations, particularly with running casing and cementing. And then over longer timescales, salt creep can then impact well integrity, for example, impinging on the casing, potentially deforming casing. So salt impacts can require a very highly complicated modeling process, which can be very difficult to reliably predict because of the uncertainty on the salt properties, the uncertainty on the salt mechanical models, and the uncertainty on how the conditions are really going to be over time. So let's look at those in a bit more detail. So first of all, stress variations around salt. So elasticity, as I mentioned, a principal stress must be perpendicular to a boundary of any major mechanical discontinuity. You see this in the field. If you look closely at a lot of fractured rock outcrops, you'll often see that a later fracture will curve as it approaches a pre-existing fracture, so that the intersection of the fractures is roughly perpendicular. If you've ever looked over time at how fractures propagate through glass, if you have a broken glass panel and you see the stress creep, the fracture grow over time, as it approaches the edge of the window or the edge of the glass, it will tend to curve so that it sort of intersects close to perpendicular. So the stress is deformed by any major mechanical property contrast, and the size of that is largely related to the size of the discontinuity. So a well, for example, drilling a well is removing a cylinder of rock. So when we drill a well, we essentially remove a cylinder of rock from the earth. That hole that's filled with fluid is a major mechanical property contrast. So that the drilling of the well deforms the stress around the wellbore, which can concentrate the stress in some parts of the wellbore, reduce the stress in other parts of the wellbore, and that can be associated with causing wellbore instability, shear failure, for example, at the wellbore wall, or fractures at the wellbore wall that can result in losses. And that deforms, if you have a wellbore that's 12 inches, so about 30 centimeters in diameter, that can deform or impact the stress state out to, say, 1 meter or 3 yards from the, 3 feet or so from the wellbore. A salt IPA is a much bigger version of that. We have a very large mechanical property contrast that can impact the stresses in the rocks around the salt for a very wide region around. Now, when we do geomechanical modeling, we make another very common assumption, which is that the Earth's stress state tends to be Andersonian. So we have either a strike slip or a thrust or a normal faulting stress regime. In all of those, we're making an assumption that one of the principal stresses, one of the key stresses in the Earth, is vertical. That works pretty well in most parts of the world. I mean, the biggest force acting on the Earth is gravity, and stresses are generated by the forces acting in the Earth. So if gravity is the biggest, it makes sense that one of the biggest stresses and the principal stress tends to be close to vertical, tends to be vertical. And so that's why we have in the Andersonian stress regime and its associated faulting, thrust faults, normal faults, strike slip faults, one of the principal stresses tends to be vertical because the principal stresses have to be perpendicular to each other. If one is vertical, the other two are horizontal. And when we build mechanical earth models, that's what we calculate. We calculate a vertical stress, minimum horizontal stress, a maximum horizontal stress, and all the other different properties. But just as the old tenet goes, that assumptions are the mother of all stuff-ups. It's when the assumption doesn't hold that we need to be very, very cautious, because that's when things can go wrong. So if we assume, for example, that rocks are elastic and salt isn't, then the assumption is not valid, and so issues can arise. Same with the stresses. If we assume that the stresses are Andersonian and the vertical stress are principal stress, but the salt deforms the stresses, disturbs the stresses around the salt body, causing the principal stresses to become tilted and inclined, so the vertical stress is not a principal stress, that makes it a much bigger challenge for doing our geomechanical predictions, which are then essential to understanding things like wellbore stability, or how to avoid sanding issues, or how we might do water injectivity to help drive hydrocarbons out of the rock. So salt can potentially impact the rock, the stresses for a long way around it, and it's very difficult to predict. Really, the only way that we can try to do this is to build mechanical, big 3-dimensional, 4-dimensional models of the salt and the surrounding rocks to try to really understand how the salt will impact the stress in the sequences around it. But of course, like all models, they're wrong. We're making a lot of assumptions, and we can only put so much resolution into it. So it's more of a guide to understanding the complexity rather than being a truly predictive method. And what we find with these changes in the stress is that we observe stress orientations and stress magnitudes potentially changing significantly above and below salts and near salt bodies. This can impact a lot of things. This can impact the optimal stress, the optimal drilling direction. It's a very common rule of thumb is that the best direction to drill is in line with the minimum horizontal stress. In a normal faulting stress regime, that tends to give the less stress acting on a wellbore, on a deviated well, and so it tends to give a more stable wellbore orientation. It could be different in strike slip and different in reverse faulting regimes, but with most sedimentary basins being normal faulting, a typical rule of thumb is to deviating towards the minimum horizontal stress will give you the most stable borehole. However, if the minimum horizontal stress is one direction above the salt and a completely different direction below the salt, your stable drilling direction is varied. If we're looking to figure out what's the best perforation direction to drill, what's the best directions to perforate our well so that we can have a stable perforation tunnel and have less sanding issues, that can vary as well. If we're looking to do hydraulic fracture stimulation, where the hydraulic fracture tends to propagate in line with the maximum horizontal stress, that can vary from place to place, depending on how the stress is being disturbed by the salt body. So structures generated by the salt, and so not just the salt itself, but also the surrounding structures generated by the salt body, such as anticlines and other things that might be overlying the salt, can will impact the stress disturbance, will cause a disturbance in the stress field, and can cause additional weaknesses such as wellbore instability through steeply dipping beds. And these mechanical earth models, when we build them, they take a long time. They can be quite complicated to build. It's very challenging to do it well. And it's all still related to how much uncertainty we have on the geometry of the salt and the mechanical properties, which we often have very little control. Just to give you some examples of how the stress can vary around salt bodies. So first of all, over on the right here, this is an example from the Nile Delta, where we have in this field, we have an approximately 200 or 300 meter thick zone of Messinian evaporites. And above the evaporites, where actually, if you look on the bathymetry, you can actually see rafting, all the blocks of sediment sitting on top of the salt, rafting down the continental slope. Above the evaporites, the maximum horizontal stresses that we observe on image logs from things like borehole breakouts are all roughly north-northeast, so south-southwest, so roughly north-south to 030 direction. But below the evaporite, the maximum horizontal stress is roughly perpendicular to that. Below the evaporite, we go into a completely different stress field, where the maximum horizontal stress is now roughly east-southeast, so almost perpendicular. What that means is the most stable wellbore orientation above and below the salt is different, and this can actually have impacts on the completion strategy we might use and on the case and the development design we might use. Over here on the left, we've got a nice example of maximum horizontal stress this is actually the anticline overlying a salt body. So this is a salt cored anticline in the central North Sea. And we're dealing with actually the sediments that are stratigraphically significantly above the salt. The salt causing an anticline above it has caused a gravitational stress disturbance in the sequences above the salt, which results in a radial stress pattern. So we get measured present day stresses, maximum horizontal stresses that are roughly perpendicular, radiating out from the center or from the core of that anticline. Salt will tend to detach the sequences above it so that we have a very different stress regime than the sequences below, as well as many people know, very different tectonic and structural styles. And the characterization and eventual prediction of stresses and mechanical properties from salt really requires a lot more focused data collection efforts. So we really need a lot more data collected in the sequences above salts and below salts and near salts in order to try to better understand these features. The last topic I want to talk about is salt creep and solubility. So as we've mentioned many times, salt behaves as a viscous fluid. How are we doing for time? Okay, all right. Salt behaves as a viscous fluid. It can flow, it can creep. And certain salts, what we call fast creeping salts, can actually flow over the course of minutes to days to hours. So we can see flowing of rates of millimeters, several millimeters per day. That might not seem like a lot. A few millimeters might not seem like a lot in a day. You know, if you sit it on your desk, you're not going to really notice a few millimeters. However, when we're drilling a well, we're dealing with a very narrow hole, and we've got to put a lot of things down that hole. We've got to put the casing down, we've got to put the drill string down. There tends to be a very narrow gap between the outside of the things we're putting in the hole and the edge of the hole. And we need a gap because we need to be able to flow fluid around that, whether it's drilling mud or whether it's cement around the outside of the casing in order to lock the casing and seal the casing in place. So those few millimeters a day can really have a significant impact on that very narrow gap that we have between the edge of the wellbore, the rocks, and the outside of the whatever we're putting into the well, particularly the casing. And what we find is that potentially in certain really fast creeping salts, that gap can start to close within days of the well being open. So salt creep can cause a constriction or closure of the little annulus that we have that can then impact the running, particularly the running of casing. Sometimes it impacts the borehole, but the drill string, but tends not to. We can usually also drill through that or back ream out of that. But particularly when we're running casing and then we want to cement, and we need to get good flow of cement up the back of that casing so that we can then cement and seal off that annulus and keep that casing and the shoe with good integrity. Any sort of impingement and constrictions can cause channelizations in the cement that could mean that we don't have a good seal or good casing integrity. Over the course of months to years, that continual creeping of the salt can in some places even impact the casing integrity. So it can even cause damage or potentially damage the casing. The key controls on salt creep tend to be fabric, so grain size, layering, all these things can impact salt creep behavior. Purity, in generally the more pure, the more mineralogical salt is, the greater creep due to more crystal faces. What tends to be a bigger issue though is composition. So some salt minerals, particularly things like carnallite, and when salts have very high water content, internal water content, they have potentially to have quite rapid creep. Creep also increases with temperature, and it also changes with applied stress. So the rocks will behave more elastically under higher stress, more elastically under lower stress, and more plastically under high stress. And finally, in addition to creep, salt also is soluble in water, and we can dissolve salt from certain drilling fluids that can cause washouts and ledges. That can also impact drilling operations and can cause particularly casing to get hung up on. A lot of these issues really come back down to being able to understand the salt, predict how much time we have before we're likely to face issues associated with salt creep, and then how to manage that, whether it's we drill the sequence quite quickly so that we can get the casing down before those issues, whether it's using increased mud weight to reduce or to minimize the creep. Cooling of the mud can also impact the creep, as well as affecting solubility. Using SBM or slightly undersaturated water-based mud can improve the issue or can minimize issues with solubility. So just to finish up, just to summarize, geomechanics and pore pressure issues associated with salt there's lots of challenges and lots of issues. They're associated not just with the geology and geological challenges, but also with data collection and acquisition of data and being able to image the sequences and trying to collect data in those sequences. Salt can be a very it can seal high magnitude pressures. It's a great seal. Salt can have complicated internal and adjacent structures that enhance encountered overpressures. We can have rubble or gouge zones that can have losses or wellbore stability issues. And salt impacts the geological and geophysical models that are the critical inputs for doing pore pressure prediction, as well as other geohazard detection and avoidance. The salt disturbs the stress state. It doesn't just impact the rocks immediately around the salt, it can impact the rocks for kilometers away from the salt body, causing rotations in the stress field with variations in stress magnitude and orientation. Salt's mechanical detachment that can cause complicated stresses in the overlying sequences. And the structures generated by salt can also promote wellbore instability. Modeling tends to be quite complicated and results in very high uncertainties. And the greater the uncertainties, the greater the challenges that we face in constructing that well and operating that well. And then finally, creep and dissolution. Salt can creep even over hours to days that can impact particularly well completions. And dissolution could cause losses, washouts and ledges that also impact well operations. Resolving the drilling issues and the issues we face with pore pressure geomechanics is a multidisciplinary issue. It's not just about how we depict the pore pressure. It also has to be about how all of those inputs that we have. So we need increased data, focus on data collection, on prediction inputs. We need enhanced specialized modeling practices, as well as improved management of hazards and uncertainties. And we need greater input and greater contact and engagement with all of the wonderful geologists and structural geologists and specialists in the salt that help us understand the geological properties and the geology around the salt. So thank you very much. How does it normally work with questions? Do you want me to
Do we have some questions?
I can see a few in there.
Yeah.
That was great, Mark. Thank you very much. Really enjoyed that. I'm just conscious of the time. Are you happy to stay for a little bit over the hour mark to answer some questions?
Sure.
Fabulous.
Sure.
Cool. All right. Well, if anyone has any questions, please do stick them in the Q&A. We've got a few in already, so I'll just get started on them. Our first question is from John Davies, and he's asking, does anyone put out a large seismic receiver array to record the energy produced by the bit while drilling?
I'm not sure. We certainly have behind the bit seismic that can be used in some places to sort of detect and do sort of look ahead seismic. We also have, of course, have measured the various properties on the drill string and how the drill string is acting as we drill through the rock that can sometimes tell us a bit about the mechanical properties. There's a lot of work being done on how to potentially use that in real time to get better estimates of mechanical properties, but I'm not sure about surface or seabed arrays detecting the drill bit while drilling. I'm not aware of any of that.
Fantastic. Our next question or point is in from Mark Rowan. He apologizes, but he would like to clarify an issue. When we look at outcrop, we do not see near salt shear zones or highly fractured zones next to salt, except, there we go. Except in very rare instances, we often see folded strata, which of course can have faulted fractures, but nothing excessive. Instead, we see slumped carapaces adjacent to or beneath salt bodies.
Well, I trust Mark on that. I mean, yeah, it's certainly widely reported that we have shear zones and things near salts, but yes, it could be one of these things that's gone through the industry, but it's not really true. So I absolutely trust you on that, Mark. So, but it's a comment rather than a question, so I can't really answer anything.
Fantastic. Okay, our next one in is from Marisol Pinzon. How is the pore pressure behavior of allochthonous salt bodies which contain hydrocarbons?
I'm trying to figure out what you're really asking there, I'm afraid, Marisol. So I'm assuming you mean like the rafts that we can get inside salts and the pore pressure. We do tend to see quite often very high pore pressures inside those. So including the ones with hydrocarbons.
Cool. If you want to build on that question, Marisol, feel free to send us in another one.
Feel free to rephrase that. Sorry.
Our next one is from Civic Sen. Hi, Mark. How do we represent variable SH max orientations above and below the salt interval in the world stress map plot? The latest world stress map release does not give such detail on how such special cases can be resolved.
Again, there's the different ways in which you look at the world stress map. So obviously, if you just get the map, there's only so much information you can plot on a 2D image. However, below that map, all the other details. So you can, if you download the world stress map into Google Earth and you click on an indicator, you get a lot more information about that indicator. And there could be potentially notes and things about variability. Often we see a scatter. So one of the ways that you often can identify whether there's a lot of variability around salt is that you look at that indicator and it's got a lot of breakouts, but a very high standard deviation, which indicates that the breakouts are not all in one direction. They're all in lots of different directions. In some instances, you might actually see two symbols on the same point. So for example, that example I gave in Egypt, we actually have, for those wells, we actually have two indicators. We have a above salt and a below salt indicator in the world stress map. So that well will have 2 stress indicators, and the details in the database actually tell you that one's below the salt, one's above the salt. It's where you have to start looking at the depth. So of course, at the large global scale or even basin scale, it's very hard to tell just looking at a map. But the key is that for the 6 or 7 things we can actually plot in the world stress map on a map, for those, there's another 20 or 30 or 40 different bits of information that are in the database. So it's usually very important to also look at the database. Does lymphostatic stress with pore pressure is equal to 0? So you sometimes see it in 2 different ways. Like some companies plot pore pressure in salt as 0. Others tend to plot it as lithostatic. Strictly speaking, if we consider the salt to be a viscous fluid, the pressures and the stresses should be all equal inside that. And so, you know, it's probably strictly speaking more realistic to put it as being the lithostatic. But in general, you're not really seeing any pressure because there's no permeability.
Lovely. Next question is in from Gonzalo Calvo. Do non-salt evaporites, gypsum, and anhydrite generate similar features and processes?
They actually have their own sort of things. Now, I'm not an expert on gypsum or anhydrite, but I do know that they can be associated with pore pressure issues. The transition from gypsum to anhydrite can be associated with an improvement in seal that can trigger an increase in the pressure underneath it in a very similar way. I mean, geochemically different, but in a overall very similar manner to why we tend to see an increase in pressure when we go through the smectite-oolite transition zone. But I'm not sure about gypsum or anhydrite as for other hazards.
Fantastic. Next question in from Tiago Alves. Mark, as with carbonates, which are markedly different depending on their age, mineralogically and biologically, can salts of different ages behave geomechanically differently? Are there generic mineralogical differences amongst, let's say, the Luan salt in the Jurassic and the Gulf of Mexico, Permian North Sea salt, Miocene med salt, for instance, perhaps due to burial depth?
I would suggest that they can all behave differently, and even salts of the same age in the same basin can behave differently. So, you know, the salt can vary quite a lot spatially. You know, we know that it's not just one simple blob of salt, that it's got a lot of chaotic aspects. So it's got a lot of layering and a lot of other impurities and a lot of other stuff inside it. And so you have varying mechanical properties.
Fantastic. I'm going to hand over to Nawaz now. I've got to bounce, but thanks again, Mark, for a great presentation. Nawaz will continue the Q&A from here on out. Cheers.
Hi, Mark. Yes, we have a question from Sufyan. Thank you for an excellent presentation. In your last slide, you said the requirement is the increased data collection. Which kind of data?
Everything we can get, but I mean, there's lots really. I mean, it's important to sort of collect more pressure data. So, you know, we can now put formation pressure while drilling measurements on the tool string, so that we can actually collect pressure measurements as we go. That used to be mostly done as a wireline log, so it was only done after we drilled hole sections, and due to its cost, tend to be focused only on the deepest hole sections where there's reservoir. But with formation pressure while drilling, if we have zones of permeability, we can take measurements at greater length along the reservoir, along through the well profile. We also should collect more core. And, you know, one of the fantastic things that's come about in the last sort of decade or so has been the development of large diameter sidewall cores. So, geomechanics can't really use normal sidewall cores. The core plugs are too small for us to really use for most geomechanical tests. So typically we've needed whole core, you know, where we actually put a coring bit down, we drill a long core. But of course that is always focused on the reservoir. No one really bothers with coring the overburden. So if we get any shale or any non-reservoir rocks, it's usually just through luck, or just because they've decided to stop and start coring a few meters above the reservoir. So we tend to not have any actual rock samples that we could take to the lab and break, because that's what geomechanics is, it's just studying how rocks break, to actually get properties. However, with the advent of these large diameter sidewall core plugs, that actually allows us to now take core specifically for geomechanical purposes at numerous different formations and spots in the well profile. So those large diameter cores, you know, they're over an inch in diameter. They're 2 inches in diameter. We can take those. We can do subplugs from them. We can do measurements on those. We can combine that with image logs. Image logs are also brilliant. High resolution and particularly cross-pole sonic dipole sonic logs are also fantastic. Lots of different things, but it's and doing more fracture tests. So actually cracking the rock to such as mini fracture tests to actually measure the stresses, the minimum horizontal stress. So all the things that allow us to actually get a better understanding of the rock properties and also understand or constrain stress and pressure in the earth. And that's just stress and pressure. On top of that, we want to better understand the geology. And so, of course, all the different things we can collect in the overburden to better understand the geology.
And we have another question from Eric Scott. He comments the talk and he says, most of your examples are offshore. Are there any differences to these concepts when you drill onshore?
Not really. You know, drilling onshore in salt basins also has very similar challenges. You know, we tend to not have the same issues. Drilling deep water has its own complications because we have a narrower margin between the fracture gradient, the wellbore stability line, and the pore pressure. And we have less of an issue in shallow water and onshore. But if you drill onshore salt bodies, you can still have significant issues.
We have another question from Andres Mora. He says, from all impacts that you mentioned that salt has in geomechanics, which one do you think are more important in the precise case of Brazilian Santos and Campos basins?
I'm not sure. We're of course looking into that as well because we have acreage in Brazil, but you know, there's a lot more work that's been done by specialists, and I would particularly recommend looking at some of the work done at the universities there, like PUC. I know has a significant group of geomechanics experts there that have been focused on looking at salt and salt geomechanics for a while. So, and there's some other salt specialists in working in Brazil for a number of years.
We have one more question from the chat that was quite earlier. This is from Beheki from Petronas, Mexico. He says, if you can brief on the workflow of building the geochemical model of salt structure, why we need 3D model of complex structure?
So we don't always need it. It really comes down to everything's got to be fit for purpose. So just like most workflows, it needs to be fit for purpose. You need to do the work that's required for those specific conditions. So and also, of course, with what's available. So if there's, you know, unfortunately, because of the lack of input data and the lack of and the significant uncertainty we have on a lot of both geomechanical properties and geometry of the subsurface near salt, it means that any models we do will have significant uncertainty as well, and sometimes so much uncertainty that they're almost not worth doing. So it really comes down to case by case. So if it's a very complicated, you do different amounts of work for your fifth or sixth well at a field where you've got a really good control on the stresses and the pressures already, and you've got drilling experience, you know better about what you're going to encounter than you would do on a rank wildcat where the nearest well is 50 kilometers away and you have very limited knowledge. So every well is different. You've got to treat every well different. There's no one workflow. You have to look at each one with what you could do and how you should do it.
Yeah, one more question. This is from Riyad Ahmadi. He says, you deal about salt structure, but how about salt in place? Has it the same consequences?
I'm assuming you're meaning salt that hasn't mobilized. So yeah, salt isn't. That's my guess, and I apologize if I've misunderstood the question. But many of the things, so some elements of the talk will apply and some won't. So for example, if there's less movement of the salt, there's less likely to be deformation of of rocks around caused by that movement. It's less likely to be fracturing and other things that might happen because you're not going to have those sorts of events haven't occurred. However, even salt that's essentially just sitting there will still be a mechanical property contrast. It will still it can still act as a detachment surface. It can still impact the stress state around it. It can still impact the tectonic structures that form above it. So there are those sorts of issues. If it's if it is a high creep salt, it's surprising it hasn't kind of deformed or mobilized, but it does still have that potential. So it really, again, comes back down to some of those will be relevant and some won't. Which ones are associated more with the salt movement, causing or generating those hazards, and which ones will be static and will be there regardless.
We don't have any other questions now. Thank you very much for an informative talk, and I learned a lot from it. Thank you for your time.
My pleasure. Thank you.
Thank you. We'll have a recording soon uploaded on the YouTube. Okay. See you, Mark.
See you, everyone. Thank you very much for inviting me.
Bye. Thank you.